Good morning. Welcome to Krishna's classroom. Now we continue with our explorations towards the fundamental theorem of calculus. Last time we introduced what are called functions of bounded variation, and proved a very remarkable theorem, namely Jordan's theorem, which says that every function of bounded variation on a compact interval can be written as the difference of two increasing functions of bounded variation. The very fact that these functions are increasing on the compact interval assures that they are differentiable. So these two components are differentiable almost everywhere. I mean, it's not that they are differentiable everywhere, but they are differentiable almost everywhere. Now, since differentiation is a linear operation, it immediately follows that all functions of bounded variation on compact intervals are differentiable almost everywhere. Now this is what we proved. Okay. Then we also proved that the derivative is integrable over the interval AB, where AB is the compact interval on which our discussion takes place. Okay, so that's it. Now we start from there. So this is what we started. Let So we had what are called functions of bounded variation denoted by BV AB, denoting the functions of bounded variation. See how we have defined functions of bounded. Then we had we proved that by Jordan's theorem, if f BVAB, then f is the difference of two functions of bounded variation. Actually, it is a very constructive proof. Bounded variation on AB, say H which are increasing on the interval AB. This is what we have. So F is the difference of two functions of bounded variation, and G and H are increasing. Therefore, that implies F derivative exists almost everywhere on AB. It's a very nice conclusion. Further, he proved that integral a to b f derivative exists. See, our objective is to prove, to find functions for which integral a to b that is proving the fundamental theorem of calculus. Okay, but this actually falls short of. This is actually, you can show that this exists and you can give a say less than k, where k is determined in terms of integral of g derivative and h derivative. Okay, so see the details. Yeah. Now, one can also see that there exists functions of bounded variation PVAB, but fails to satisfy. This is the relation star. That means functions for which the fundamental theorem of calculus is not valid. I think we have already discussed it. If not, we will do it later. But let me now try to go a step further and possibly define a new class, namely absolutely continuous functions on A. Okay. You see that the problems of differentiability comes from rapid oscillations of the function. Okay. Now, incidentally, you also recall that we analyzed sin x, which is a function of bounded variation, how it is actually obtained as and what is the corresponding the decomposition that you are talking about in the Jordan's theorem in the case of the function fx equal to sin x on the interval 0. That we have already seen. So we get an idea how things work. But what happens is that the difficulty comes from the rapid oscillations. In fact, this is something which you can eventually prove. See, fascinating examples for this kind of things is given by the function fx defined as x to the power alpha sin 1 by x to the power and 0. So for x and 0 at now the relative values of alpha and beta are relevant in the in this function becoming a function of bounded variation. So this is very important. Okay. Now we shall have a discussion of this later. Now here what is happening is that, see, we take both alpha and beta positive. Now oscillations are coming out from the term 1 by x to the power beta, and you see that this is where you get this, that is 1 by x to the power beta equal to n pi by 2. For all values 1, 2, 3, etc., n equal to 1, 2, 3, etc., what happens? Then you see that suppose this condition is satisfied. Sorry, I think 1 by n pi by 2. Then you see that the values the sine function takes at these values for n belonging to n are either 1, either plus 1 or minus 1 or 0. So they take values, say at n equal to 1, it is going to be pi by 2, so you get sin pi by 2. Yeah? At n equal to 2, you will get 0. At n equal to 3, you are going to get minus 1. So that means that oscillation is, see, I will mark this x to the power beta equal to, so you see, 1 by or x equal to n 1 by 1 by pi by 2 to 1 by beta. And as n tends to infinity, now you see that this goes to 0. So the distribution is something like this. So when n equal to 1, you get pi by 2 to the power 1 pi beta. Then 2 pi by 2 or pi to the power 1 by beta, etc. It will go like this. So this is n and so on. So you see that the function or this part of the function, since alpha is positive, see, it is bound by the function x to the power minus, what is it? X to the power alpha. So you see, because of the oscillation, it is going to be bound by x to the power alpha and minus x to the power alpha. So you have two branches. For example, x alpha equal to 2, say, then this is going to be, this is the case when you take x square. So the oscillation will be within this. Okay, and what you have is, at this point the function takes the value 1, or I would say x square. Now in the next point it is going to take the value 0. So the function is moving like this, and then it takes, at the next point it takes the value minus x square, where x is given by this number, and so on. So you see, this is the market. So what you have is, when you work out the variation over a partition where we have choose this set of points, eventually the question would be to the following. So you have the problem, the following problem, namely whether for some sigma that you can work out is that is the question. So for what values of sigma this will happen? So if sigma is greater than 1, then you see that this sum converges. I am deliberately keeping things for you to work out, not going to the details of the construction, but just giving some hints. Now you see that 1 sigma 1 by n to the power sigma So use this. And this sigma would be determined in terms of both alpha and beta. So it will be the values. So you can determine the relative values of alpha and beta that would make you satisfied. So here both alpha and beta are positive, and if they find out under what conditions, this would be the sigma, how sigma is determined in terms of alpha and beta, and then the problem boils down to whether the convergence of this series. Okay, right. So I'll leave that. So I leave the details construction to you. But it's a fascinating and important example because that demonstrates the sort of problems that you encounter with oscillations. So it's the rapid oscillations that are going to bring in problems. Okay. Now we try to construct a much more stronger condition than the function being of bounded variation. The stronger in the sense that now you see we found that we still fail to satisfy the fundamental theorem of calculus. So suppose you put more conditions on this class. Will you get the fundamental theorem of calculus being satisfied? And this is the objective. With this objective, what we do is we are now going to introduce a new class of functions, namely functions which are absolutely continuous. So we have the absolutely continuous on the compact interval A, which we designate by AC Let us go to the definition. A real valued function closed bounded interval is said to be absolutely continuous maybe provided for each positive there exists a delta positive such that for every finite disjoint collection collection these are open intervals. Okay, for k equal to 1 to n of open intervals, maybe we have sigma k equal to 1 to n f less than epsilon whenever the total length of such intervals, that is less than delta. See, it's a variation of your definition of continuity, as the name suggests, of course. Okay, what is the continuity, or okay, what is the uniform continuity of f on the interval AB tells? If you take any subinterval, okay, xy, okay, you have mod fx minus that means given epsilon there exists a delta such that for every x and y you have mod fx minus mod fy is less than epsilon, mod fx minus fy is less than epsilon whenever mod x minus y is less than delta. That means the variation of the function on any interval of length less than delta is going to be less than epsilon. So here what we are saying is it is much more stronger. Therefore, clearly you see that this definition implies the function which is absolutely continuous is uniformly continuous on AB. So let us just make note of that. In fact, absolute continuity tells much more. Says on the interval AB, if you choose subintervals, not necessarily continuously distributed or any such thing, so that the total length of these intervals is less than delta, then the variation of f summed up over this is going to be less than epsilon. That means, given epsilon, there exists a delta such that, and a set of, and for any choice of subintervals, open subintervals which are disjoint and having their total length less than delta, you would have the total variation of the function on these intervals coming to, being less than epsilon. Now we give an example. We said that f absolutely continuous implies f is uniformly continuous. Now we want to assert that the converse is not. Okay, absolutely continuous continuous. The converse need not be true. Often in these kind of situations, you will have to look at some pathological functions, there are many such in our treasure for analysts to pick on and analyze. And one such fascinating function is the following. Look at the following example. The Cantor-Lebesgue function I request you to go back and refer to what Cantor-Lebesgue function is. Is increasing and continuous. Increasing and continuous. 1, 0. But it is not absolutely continuous. What is this function? Let us give a quick view of this. Let and in the nth stage of construction of the Cantor set, how do we do this? Let us see. We take the interval 0 to 1, drop the middle 1/3, drop this part, and then you are left with two close bounded intervals. Once again, you take the middle 1/3, drop that. That is at the second stage. You get four such sets and so on. And then now for each one of them, you drop the middle 1/3 and so on. Continue this process, and then you are left with something. Okay, and you see that you are left with what is called the Cantor set. Okay, the Cantor-Lebesgue function is something fascinating, and when you, while constructing the function phi, this we have discussed in some detail earlier, so I don't want to recall it because you need a whole lecture to really look at this function. A disjoint collection subintervals k running from 1 to 2 to the power n. As we have seen in our process, the first stage, when n equal to 1, you are leaving out 1 by 3, 2 by 3. Okay, so you are left with two such sets in the first stage for n equal to 1. For n equal to 1. For n equal to 2, you are left with four such sets, that is 2 to the power n. Okay. For n equal to 3, you are left with 8 such intervals and so on. So we are marking these as, and the such of 2 to the power n disjoint subintervals. Disjoint. Okay. Of 0, 1. So at the nth stage, we have 2 to the power n compact subintervals each of length 1 by 3 to the power n. That you can easily work out. Okay, go through the Cantor construction. The Cantor-Lebesgue function phi is constant on intervals which form the complement of therefore phi is increasing and equal to 1. This is the crucial part. Now choose equal to 1. You have sigma k equal to 1 to 2 to the power n of dk minus is equal to 2 by 3 to the power whereas this is equal to 1. So it's a monotone increasing function from 0 to 1. Okay. So what does this say? Thus, given epsilon positive, epsilon equal to 1. That is, we are now making the choice of epsilon equal to 1. There does not exist a delta positive such that the condition of absolute continuity why? Suppose there exists such a delta, then delta is positive. See, delta is positive, therefore there exists an n such that less than delta. Okay, and you have these intervals taking care of all the points where the function is increasing. That is, the entire Cantor set is taken care of by the sets Ck, Dk. Okay, therefore you see that you cannot choose a delta such that for all values, or you cannot choose a number such that for a delta such that for which you have this sigma k equal to 1 by 1 to 2 to the power n is less than 1. That is not possible. So the condition of absolute continuity would fail. Okay, therefore this function is not absolutely continuous. It's an increasing function. It's a continuous function. It's not absolutely continuous. Now it's quite easy to see that this function is of bounded variation. There's no difficulty because you see you have an increasing function on the interval 0 to 1. It starts from 0 and goes all the way to 1. Okay, and you can easily see that the total variation of this function is equal to 1, and therefore this is a function of bounded variation, but it's not absolutely continuous. So this is phi is equal to 1 belongs to PV0, but that's also an example of a function which is a function of bounded variation, but not a function of function which is absolutely continuous. Now we shall see the relative relationship between these concepts. So apparently absolute continuity puts more stringent restriction on the function than the bounded variation condition. So we now start exploring this. What happens to this? Yeah. Yeah. So we make some remarks. Linear combinations of absolutely continuous that's quite easy to see. However, if you take the composition of two such functions may not be absolutely this. Composition of absolutely absolutely. Now we give an example here. Define f from -1 to 1 r by the cube root of x. Now g from by you can easily see that this is an onto function from -1 to +1 to -1 to +1. X so that's the definition of G. Now G composition F does not belong absolutely continuous on the interval -1 to 1. You see that G composition F is well defined because F is a one-to-one function. It's well defined. Okay. Therefore, G composition F is defined. In fact, more explicitly, I can write this G composition F two by three zero, and this is 0. Suppose x belonging into 0 for 0. Now you can work out with the partition and check this. Choose Pn, a partition of -1 to +1 as -1, 0, 1 by 2n, 1 by 2n minus 1, 1 by 3, 1 by 2, 1. Choose this partition and then analyze this function. You can show that this is not an absolutely continuous function. It's another example of a function which is not absolutely continuous on the interval -1 to +1. Okay. So we got some insight into absolutely continuous functions and functions of bounded variation order. Now what we prove is, do you have a large class of functions which are absolutely continuous? So we prove the following theorem. If f is a function Lipschitz on a bounded interval AB, now this is quite easy to prove because let be a Lipschitz constant so that this is the Lipschitz condition for every AB. This implies sigma the criteria for absolute continuity. Let's just check. The criteria for absolute continuity is this. k equal to 1 to n is less than delta implies f is less than what? It is going to be less than c times summation, and that of course is that of course is, which is less than see, this is c times what is it? Yeah, okay. And that I am writing, rewriting this, and c times epsilon by therefore you see that for any partition, see, any partition with the property in I joint AB given epsilon So that proves the absolute continuity of. Okay. So that is probably a nice place where we can stop, and probably with a remark. Want to make a remark? There exists so example is